So from the telegrapher equations, we've determined the total current at every location on our transmission line from a value of Z is equal to 0 back to a value of Z is equal to minus L. Likewise, we know the total voltage along a transmission line at each and every point between one end and the other. But instead of talking about total current and voltage, or even plus wave voltage and minus wave voltage, instead we can go through and think about power, rate of energy flow. At what rate is energy flowing down our transmission line? And of course, we can determine that from the knowledge of the current and the voltage. The expression for rate of energy, this is time averaged rate of energy flow, power. It's the same expression that we've used before. Of course, it was in terms of an index at some port plane. In this case, our port plane is simply defined by our index Z. If Z is equal to minus L over 2, we'd be halfway between the two ends of the transmission line. And we could then determine the rate of energy flow across that port plane by inserting the value Z is equal to minus L over 2 into this expression. And of course, we could do that for any location, any index Z. So this then is the rate of energy flow, joules per second, at some arbitrary location along our transmission line. Again, we draw a port plane and we asking ourselves at what rate is energy flowing across it. We can determine it by multiplying the total voltage times the complex conjugate of the total current. We take the real part of that result and then divide by 2. Let's first start out by examining the product then of the total voltage with the complex conjugate of the total current. And again, this complex conjugate is very important. So we write the total voltage expression here from telegrapher equations in terms of the complex wave amplitudes V0 plus and V0 minus. Notice I've left off the subscript or the function with respect to omega. That's implied now from now on. This is the expression for the total current along a transmission line, and of course we take the complex conjugate of that. Now I'm going to show in detail this operation of determining this function because I find that students frequently struggle with coming up with the right answer, and it really comes down to the idea of complex arithmetic, complex math, taking the complex conjugate, for example, of a value, recognizing what is a complex number and what is a real value. So we go through and we take the complex conjugate of this result. And so what we're really doing is going through and taking the complex conjugate. The complex conjugate of the product of two complex numbers is the complex conjugate of each. So we need to go through and find the complex conjugate of this and this, for example. When we do that, we find V0 plus is a complex number, so we have to take the complex conjugate of V0 plus. We can't leave it as 0 plus. And again, this is a mistake students frequently make. V0 plus is not a real value. It's a complex value, so we need to take the complex conjugate. In contrast, Z0, of course, as we look here and it's left unconjugated, really we have taken the complex conjugate of Z0, but for a lossless line, the Z0 is a purely real value. And of course, the complex conjugate of a purely real value is the same real value. The complex conjugate of 2 is 2, so the complex conjugate of Z0 is Z0. Once again, contrast that with the complex conjugate of complex number, V0 plus, we get the complex conjugate of V0 plus. We can't say anything more than that. Same thing for V0 minus, we have the complex conjugate. Complex conjugate of Z0, of course, is Z0. What about the complex exponential terms? Well, we have e to the minus j beta z. To take the complex conjugate, we simply replace the minus j with a plus j. For the e to the plus j beta z, we replace then the plus j beta z with a minus j beta z. That's the complex conjugate of those complex exponentials there. So this is the reduced form then of the complex conjugate of the total current. Notice we haven't done anything to the total voltage since we didn't take the complex conjugate of that. Now we multiply these two results together. We have two terms in the first product term, we have two terms in the second product term, so we multiply them through and we get 4 terms. In the first term, we multiply v0 plus and the complex conjugate of v0 plus. And again, it's very important that you understand if I multiply a complex number by its complex conjugate, we get a real value, which is the magnitude squared of that complex number. And so we have the magnitude squared of v0 plus. Frequently, students will tell me this is v0 plus squared, and of course that cannot be true. v0 plus squared would be a complex number, where the magnitude of v0 plus is a real value. Multiplying e to the minus j beta z and e to the plus j beta z, of course, we get e to the 0, and that turns out to be 1. For the second term, we're multiplying this first term here with the second term here. And so notice we get v0 plus times the complex conjugate of v0 minus. There's no simplifying that. It's as reduced as it can be at that point. But the exponentials, e to the minus j beta z times e to the minus j beta z is e to the minus 2 beta z. If we go through then and multiply the second term here with the first term, we would get this result. And finally, if we multiply this second term with this second term, we would get this result here. Notice in this case, we're multiplying v0 minus with the complex conjugate of v0 minus, which is why we get the magnitude of v0 minus squared, not the value of v0 minus squared, the magnitude of v0 minus squared, a real value. Likewise, the complex exponentials then combine to get a value of 1. So we collect terms. We're going to do this first term and the fourth term are purely real, so we're going to pull them out front, and we're going to pair these values together. And the reason we pair these values together is we see that this second term, if we take the complex conjugate, is simply the first term. This term and this term are the same term with the exception of the complex conjugate. So we're taking the complex conjugate of a complex number and subtracting from it the same complex number. What do we get in that case? Well, this turns out to be an identity for complex numbers, and it's important that you remember this identity. So here's that identity. If we take the complex conjugate of a complex number c and subtract from it that same complex number c, what we find is the result is a purely imaginary result. Basically, the real parts subtract from each other and go to 0, and the imaginary part is doubled. That's what the value of 2 is there. So this is a purely imaginary result. So we can apply this identity to this result, c being this value here and this value here, and so inserting that in this identity, we get this result for those last two terms. So we can rewrite the product of the total voltage and the complex conjugate of the total current in this form. This is the correct answer. Notice this first term here is purely real. The magnitude of a complex number is a real value. We divide it by the characteristic impedance of a lossless transmission line, which is a real value, and so this result is real, as is the second. Contrast that with the last term, this third term here. The imaginary part of a complex number is a real value. I say again, the imaginary part of a complex number is a real value. But if we multiply that real value by j, then that becomes purely imaginary. So this third term here is a purely imaginary term. We have a complex result, but a complex result that has nicely separated into two terms which are purely real and a third term which is purely imaginary. And this is going to be a great benefit for us because, of course, we need to try to extract the real part of this result. Well, the real part of this result is fairly simple. It's just this first term. So the result on the previous page, again, the first two terms are purely real. The third term is imaginary. And so we take the real part of the product of the total voltage, the complex conjugate, and the current. We simply retain those first two terms. This is the rate of energy flow along our transmission line, the power as a function of position z. Now, there's something curious here, and that gives us pause. Perhaps we've done something wrong because this function of position z seems to be independent of the position z. Notice nowhere in here do we see the position index. And this is always a problem, and students will oftentimes provide an answer like this, where we have a function of z that turns out not to be a function of z. It's simply a number. Frequently, that result is incorrect, but not always. In this case, we say the function of position z is this, simply a constant with respect to position z. And so that can occur, and this is what it's saying, that the power along the rate of energy flow, the power along the transmission line at every single point is the same value. It does not change. It's constant with respect to z. And that's what this result means, since it's not a function of position. If we were to go through and use this result to determine the rate of energy flow at each and every point along the transmission line, at the very beginning or the very begin or halfway in between or a third of the way down the transmission line or 3/4 of the way down the transmission line, what we find in every single case, we get exactly the same value because this result is independent of this location z. In other words, the rate of energy flow is a constant. Now, this makes perfect sense. In fact, if we were to get something other than that statement, that would give us reason to believe that we did something incorrect. Because the lossless transmission line is, of course, lossless. And any lossless device cannot alter the rate of energy flow. It can't increase it, it can't decrease it. Whatever the rate of energy flow into the two-port device is, into our transmission line, will be the same as the rate of energy flow at the output of our two-port device, the output of our transmission line, which means the rate of energy flow will be the same at any and every point between our input and our output. The rate of energy flow is a constant with respect to position z, and that is because that transmission line is a lossless device. It cannot increase or decrease the rate of energy flow. Now we look at this result, and there's something that is interesting that jumps at us. We have two terms, and the rate of energy flow, the power along our transmission line, is the difference between these two terms. Notice the minus sign here. What jumps at us is this first term depends on V0 plus, but V0 plus only, the wave amplitude of the plus going electromagnetic wave. The second term depends on V0 minus, but only on V0 minus. V0 minus being the complex wave amplitude of the negative going, the electromagnetic wave, the wave in the direction of decreasing z. The question then is, this have some physical significance? Again, math is the language of engineering and physics. The result of our equations is not beneficial to us because it gives us a recipe for pushing the buttons on our calculator to provide a correct answer. No, the math is beneficial because it tells us what's going on physically. What does this math tell us about what's happening on a transmission line? Well, to understand this, let's go through and determine the rate of energy flow associated with the plus wave only. If only a plus wave existed, then of course we'd only have a plus wave voltage and a plus wave current. We know the expression for the plus wave voltage, and we know the expression for the plus wave current. And so we can take its complex conjugate and multiply the two together and take the real part, and what we get is this term here. This term here, of course, is the same as the first term out of our expression. And so physically, we can interpret this result as being the first term is the power associated with the plus wave. We have electromagnetic wave propagating now in the direction of increasing z from your left to right. We also have a wave propagating in the direction of decreasing z from your right to left. Each of those two waves have an energy associated with them. They carry energy along. And the question is, at what rate? Well, this result provides the rate of energy flow for the plus wave. And again, this is the first term in our result. Let's then determine the same value for the minus going wave, the wave propagating in the direction of decreasing z. And so we determine that from V minus and I minus, and again we know those expressions. We take the complex conjugate of the current and multiply everything together and take the real value in this case the result is purely real, and we get this result. And of course this looks exactly like the result we got for the plus wave power, with the exception that instead of V0 plus we get V0 minus. This term, of course, is the second term in the power flow along a transmission line. And this is the power associated with the electromagnetic wave flowing in the direction of decreasing z. This is our negative wave power. And so let's look at these two results. Again, this P plus is defined, the power associated with the plus going wave propagating in the direction of increasing z is provided by this value. And this value is always positive. The magnitude of any complex number is a positive value. And of course, Z0 is a positive value. P minus is likewise a positive value, but P minus describes the rate at which energy flowing is flowing in the direction of the negative way, in the direction of decreasing z. So this tells us the rate at which energy is going this way, and this tells us the rate at which energy is flowing this way. Ultimately, what we're interested in is the net power flow, the difference of these two. If I draw a port plane along a transmission line, at what rate is energy flowing across it, the net power flow? We'll have some power associated with the plus wave. We have some power associated with the minus wave. What is the net power flow? So the net power flow is simply the difference between the power associated with the plus wave and the power associated with the minus wave. Each wave carries energy along with it, and therefore energy flows at a certain rate. If I take an arbitrary location on the transmission line, I want to know what the net power flow is, which will be the difference between these two, then we can calculate in this form. Of course, that net power flow for a lossless transmission line is going to be the same at every location on the transmission line. The rate at which energy is flowing into the input of the transmission line will be the same as the rate of energy flow at the output. The same as the rate of energy flow a third of the way down the line, or half the way down the line, or 3/4 of the way down the line. At every point, it's the same value. We can write it as a function of position z, but it turns out it is a result constant with respect to position z. Again, that is because the transmission line is lossless. Now, if we look at this result that we get could be positive or it could be negative. Remember, the first term and the second term are both positive, but we're taking the difference between them. If the second term is larger than the first term, of course, then we'd have a negative value, for example. So if this first term, the power associated with the plus wave, is greater than the power associated with the negative, then the net power will be positive. But if the power associated with the plus wave is less than the power associated with the minus going wave, we find the net power is negative. And again, what do we mean by positive power and negative power when it comes to net power? Well, if the net power is positive, it means that the power is flowing in the direction of increasing z, and if the net power is negative, it means that power is flowing in the direction of decreasing z. And so this is very much like current. If I say 2 milliamps, positive 2 milliamps is flowing in the direction of the arrow, and minus 2 milliamps is flowing in the opposite direction of that arrow. So it's a similar situation. The plus and minus, positive and negative, indicate a direction with respect to the flow. And in this case, there's only two directions, in the direction of increasing z or the direction of decreasing z, up the transmission line or down the transmission line. Since these results for net power flow can be interpreted in terms of plus wave and minus wave, that really says that we should evaluate this in terms of our wave viewpoint. A wave propagating in the direction of increasing z and decreasing z. We have a power associated with each, and the net power flow along our transmission line is simply the difference of the two. To round this out, of course, with respect to our wave viewpoint of transmission line activity, we have plus wave and minus wave, and of course a reflection coefficient that relates those two. So let's see if we can throw reflection coefficient in here to describe the rate of energy flow, the power along the transmission line. First of all, we know that gamma 0, the complex value gamma 0, is defined simply as the ratio of V0 minus to V0 plus. This is the value of a reflection coefficient gamma when evaluated at z is equal to 0. We can rewrite this equation in this form. V0 minus is gamma 0 times V0 plus. What about the magnitudes? That's what shows up in our power calculation, the magnitude of V0 minus, or specifically the magnitude of V0 minus squared and the magnitude of V0 plus squared. The magnitude of gamma 0 squared, therefore, is equal to the ratio of the magnitude of each of these two numbers, and therefore we can write the magnitude of V0 minus as the magnitude of gamma 0 times the magnitude of V0 plus. Of course, we could square both sides and say that the magnitude of V0 minus squared is the magnitude of gamma 0 squared times the magnitude of V0 plus squared. And with that result, we can rewrite our minus wave power in terms of the plus wave amplitude V0 plus and the reflection coefficient value of gamma 0. So V0 minus, it turns out, once you look at this result being is the V plus, V0, the power associated with the minus wave is simply the power associated with the plus wave times the magnitude squared of gamma 0. Now, one important thing to keep in mind here is the magnitude squared of gamma 0. Gamma 0 is the reflection coefficient at z is equal to 0. But the magnitude of the reflection coefficient at z is equal to 0 is the same as the magnitude of the reflection coefficient at any and all values z. The reflection coefficient has a magnitude which is a constant with respect to position. And so we say it is the reflection coefficient at z is equal to 0, but really it's the reflection magnitude of the reflection coefficient at any and all locations, since they are all the same. So we put the pieces together here, and we can say that the ratio of the power associated with the negative wave to the power associated with the plus wave, and of course each of these are real values, the result gives us a real value, which is the magnitude squared of gamma 0, or more specifically, the magnitude squared of the reflection coefficient function. And so we see the result, the mathematical result with respect to power, is most easily understood with respect to this wave viewpoint. And that's what we were talking about earlier, that we can talk about transmission line activity in terms of the circuit viewpoint, current and voltage and line impedance. But the mathematics sort of tells us that this is fundamentally a electromagnetic wave propagation. And the results in our math will verify that result. And this is certainly the case here. Given that, we can go through and say the net power is the difference between the plus wave and the minus wave. And of course, the minus wave now we can write in terms of the plus wave and the reflection coefficient function. We factor out the plus wave power and we get this result here. We can say that the net power flow is equal to the incident power flow times a value, which is 1 minus the reflection coefficient magnitude squared. And this is a very important result. This result here will always be less than or equal to 1, some value between 0 and 1. And really what this tells us is what percentage of the plus wave voltage is represented in the net power flow. The net power flow will always be less than or equal to the incident wave, the plus wave rather, power. And the reason for that is because there'll be some amount of negative wave power, power flowing in the opposite direction, which reduces the plus wave power down to a value which is the net power. All right, so this result is very important, and again, really an expression of the wave viewpoint of transmission lines.